Okay, so for this video assignment, we'll be doing two things. First, we can compare a strong base or a good base and a good nucleophile. So, draw one. Okay, so for a good nucleophile, we have iodine, and for a good base, we have OH. So there are a few things we can immediately notice. Well, they have excess of electrons. They're both anions. So they have a negative charge, which gives them the potential to interact with positively charged species, such as our protons or our electrophiles. So they can both participate in nucleophilic substitution and elimination, but they can both act as nucleophiles or bases, but there are some key differences. I mean, another similarity, they both have lone pairs of electrons. That's what makes them potential nucleophiles, because they're able to donate electrons to the electrophile or the positively charged species that wants some sort of electron density. So the difference is in the basicity versus nucleophilicity. So OH is a stronger base. It's a stronger base because it holds its electron pair more tightly, and it makes it more likely to deprotonate or remove a proton or a hydrogen. This is due to its relatively small size, and it has a high charge density on the oxygen atom, so that bond is very tight and very strong. So iodine is a weaker base because it's a larger atom and it holds its electrons more loosely. So it's farther away from, the electron cloud is farther away from the nucleus, so the electron pair is a little more loosely held. So it's less likely to abstract a proton. It makes it like a little bit of a less aggressive base, but it's a better nucleophile. And we get there because it's more polarizable than hydroxide because of its larger size. So it has a lack of affinity towards protons, but has a large electron cloud, which makes it highly reactive. It means it can form bonds more easily with electrophilic centers, making it a stronger nucleophile in this case. It would react faster than hydroxide because it's less hindered, and it's more willing to donate its electrons because they're more loosely held in the electron cloud. So the OH bond especially, that's a very tight bond. It doesn't really want to give away its electrons. OH is a weaker nucleophile, naturally, because it's less polarizable, because it has a smaller size and it's less able to stabilize during the transition state in these nucleophilic reactions. So that is the main difference between them. Similarities and differences, what make a good base and nucleophile, is a very subtle difference, but I want to make sure you can see the reaction now. It's a very subtle differences, but it is there, and you can use those things to determine. So what we have here is the reaction right above, and there's a few things that we can write down on the side to get started to determine what mechanism we're going to be looking for. So leaving group we can classify as chlorine. The nucleophile / base, that'll be right here. That'll be our O and A. Our solvent will be our OH. And then our sub will be the entirety of the rest of the structure besides chlorine. So we can do a few things to look at it. We can see what, if it's tertiary, primary, methyl. I mean, it's not going to be methyl, but we, primary, secondary. So we look at the attached carbon. We have 1, 2, we have 3 carbons attached. So we know it's going to be tertiary. What does that help us do? That means, it's probably not going to be some 2. So we can, also there's heat, forgot to mention. We have heat. So we can automatically knock off SN1, SN2. So we're right there. And now, so the fight is between E1 or E2. So we can look at what we have. So we know we have heat. We know we have a strong base. So there's a few other things. You know, we have a protic solvent, which usually means E1. Heat usually means, you know, we're heading towards E1. But no matter what, in the end, a strong base overpowers everything else. So we're looking at an E2 reaction here. We're looking at a concerted reaction. So we're going to have a one-step mechanism here. We can draw that. So first we can look at, you know, our alpha carbon and our beta carbons. So right here will be our alpha, you know. Right here will be our beta. You got two betas right there. Not right here because there's already 4 bonds at this center, so we know we're not going to have any hydrogens to deprotonate. So we can pick either side here because, you know, both of them are going to have their respective hydrogens. But for, you know, organization and, you know, everything else, we'll go down here. So there's no erasers in here. Let's kind of erase a little bit just to get some more room. So we're going to have a one-step reaction here. We have right here. So we have our first, let's see that. Bring it a little closer. Okay, so we have an arrow here from the bond to the chlorine. So the chlorine is going to take those. Chlorine's going to take those electrons and it's going to run. So we can put it over here, you know. And we know it's going to be one-step reaction, so we can find the positively charged species that's going to go with it. And if we look at our base right here, we have Na, which is our positive charge. That's going to go with the chlorine. So we got our chlorine, we got our Na, and so what's going to happen after that? So we know we're going to have an alkene of sorts here, you know, elimination. So the base is going to come over here without the Na. It's going to have, you know, our 6 electrons here, right? So then the oxygen, you can kind of think of it as one of the lone pairs. It's going to come and take that hydrogen. But first, the hydrogen, or the bond that we have here, let's imagine, you know, I picked probably the wrong hydrogen for this very angle, but we'll pretend that, so these electrons, the bond here is going to move over to the bond in between the beta and the alpha, and that's going to make our alkene. So the base is going to come and it's going to deprotonate, it's going to take the hydrogen, and so we can write that over here. You know, our next is going to be OH. 2 electrons, okay? And then we're going to have our alkene next, and we can draw that. I don't know if you can see. Okay. Okay, so that's what we're going to get. Yeah, basically, that's what we're going to get alkene. Sorry, this stupid thing. I can't. I want to make sure you can see it. Okay, so we got a one-step concerted reaction because we got E2. So it's going to form our Na, our Cl, you know, our leaving group is going to leave. It's going to bond with the positively charged species, or not bond, but, you know. And then we're going to have our base that's going to deprotonate, take the hydrogen away, so there's room for an alkene. The alkene forms, the hydrogen's taken away, the leaving group, and we're left with that. You know, we can mark this was our alpha, this is our beta. And also, it's good to note that we could have done the same thing on the other side. And we could have done an alkene on this one instead of that one. You know, you can really choose which one. So that is the E2 mechanism. That is everything. Enjoy.